This video is kind of a review of some of the stuff you learned in first semester calculus. So in Math 5A, we learned how to approximate the area under a curve using something called a definite integral, which we have written here. So this is a definite integral. And the way the definite integral worked was we approximated the area by using areas of rectangles. Okay. So the first thing that we did was we divided our interval AB into n pieces or subintervals. So let me pause the video for a second and draw a number line. Okay, so voila, a number line has magically appeared. So I wanted to point out that we're trying to find the area under this curve f of x, y equal to f of x, from the endpoints a to b. So I labeled the two endpoints of my interval a and b over here. And when I subdivide the interval ab into n pieces, I'm going to have a whole bunch of endpoints over here. I'm going to have n plus 1 endpoints, and I label the very first endpoint x0, and then I go on from there. What you'll see is that I wanted to capture a general subinterval. A subinterval is an interval contained within the interval AB. So I'm just going to call it the ith subinterval, and its endpoints are going to be xi minus 1 and xi. So when I chop this up into n equal pieces, this makes the width of each rectangle equal to, we're going to call the width delta x. And if you wanted to calculate what the width of that was, you would take the width of the entire interval, which would be b minus a, and then divide by n because you're dividing that length into n equal pieces. So I could label this width right here, delta x. Okay. Now, the height of each rectangle is going to be found by evaluating our function. So I'm going to highlight that. We're going to evaluate our function to get the height. And we're going to evaluate it at a sample point within each subinterval. So sometimes we use the left endpoint, sometimes we use the right endpoint. When we don't want to specify which endpoint we're using, we're going to call our sample point xi star. So this I part tells you that you're within the ith subinterval, and the star is just meaning we're not specifying if it's going to be the left endpoint, which would be xi minus 1, or if it's going to be the right endpoint, which would be xi, or if it's something in between. Okay, so when we don't specify, we just call it xi star. Now, in Math 5A, we looked at two situations. So those two situations that we looked at are one involving the left endpoint and left endpoint, and one involving the right endpoint. So if you look at this picture on the left over here, you can see we have our, in this case, 4 subintervals, and we're going to evaluate our function at the left endpoint of each subinterval. So when you look at the height of this rectangle, we're seeing what's the height of the curve at the left endpoint. At the left endpoint, that's going to be the height of each rectangle. If you look at the picture on the right, we have the same subintervals, but this time we're evaluating the height of our rectangle at the right endpoint. So I think you can see by looking at this picture, when you evaluate the right endpoint, you're going to get rectangles that are a little bit above the curve. In this case, we looked at the left endpoint, we had rectangles that were below the curve. All right. So I want to break down this left endpoint, right endpoint situation a little bit more deeply. So let us draw a picture of our ith subinterval. I'm going to pause this. And we're back. Voila, we have our interval picture reappearing. So when we want to do a left endpoint approximation, let's call it xi star. In our situation, the left endpoint xi star is just going to correspond to that point xi minus 1, which is, right here. That's the left endpoint of our ith subinterval. So what I want to do is I want to describe how do I represent this point algebraically. And the way that I do that is I start with my starting point of A, and then I'm going to keep adding different widths. I'm going to keep adding 1 delta x, 2 delta x's. I'm going to keep going until I get to this endpoint right here. So how many delta x's do I need to go? Well, I'm going to need to go I minus 1 delta x's. So I'm going to put an I minus 1 there, delta x's. Okay, and that's going to be the left endpoint xi star. What about for the right endpoint? Well, the right endpoint of the ith subinterval is over here. So it is basically the left endpoint plus 1 extra delta x. In other words, starting at A, and instead of going I minus 1 delta x's, we're going to go one more. So we're going to go I delta x's. So in this particular case, when I write it down, the right endpoint is just going to be xi, according to that picture I have there, and that is going to equal to A plus I times delta x. Okay, regardless of which endpoint we use, we are going to get a Riemann sum. So the Riemann sum is really just an approximation. It basically looks like the summation as n goes from 1, as I goes from 1 to n. You're going to have your f of xi star, that's going to be the height of your rectangle, times delta x. That's going to be the width of your rectangle. All right? So when you take the limit as n goes to infinity, this means that the number of your rectangles also goes to infinity. So doing that basically means that the width of each rectangle, delta x, is approaching 0. And that's how we get our definite integral. So if I took the limit as n, the number of rectangles, goes to infinity of my Riemann sums, the summation is I goes from 1 to n, f of xi star, remember that's the height of the rectangle, times delta x, that's the width of the rectangle. That's how you get the definite integral. A to b, f of x dx. Okay, so the basic idea is that when our width becomes super narrow, it really doesn't matter if we had chosen the left endpoint or the right endpoint. So when you take this limit as n goes to infinity, this delta x becomes so narrow, left endpoint and right endpoint become almost indistinguishable. All right, this was just a review of what we had learned in first semester calculus. In the next video, we'll talk about the approximate integration techniques we learned in second semester calculus. Take care, everyone.